Alright, well welcome back everyone. This example is actually one of my favorite in the class. It's one that makes us think like a practicing engineer and sometimes get away from the equation of motion development and four-step process that tends to plague us. Big help, but oftentimes gets monotonous in the context of vibes problems. This is the type of problem that I might actually run into in my own research work, and the type of thing that I often like to think about. So what we're given here is just a set of simple facts, and we're asked to find something out about the system given these facts. So here's what we know. We're told that there's a system that if we add damping to the undamped system, it causes its period to increase by 25%. Given just this little bit of information, we're asked to find the value of the damping ratio after the addition of damping. So here we're talking about a quantity that we haven't spent a ton of time talking about today. We're talking about the period of a vibratory's response. And so what I'm going to do is I'm going to first of all figure out what the T, the period of an undamped system is. Well, we know the frequency response of an undamped spring mass system is given by 2 pi divided by the natural frequency of the system, omega n. Likewise, I know that if a system is damped, the damped period of the system is given by 2 pi divided by the damped natural frequency of the system, omega d. I furthermore know that omega d is equal to omega n times the square root of 1 minus zeta squared. In this problem statement, we're told that the damping ratio after the period after the addition of damping increases by 25%. This to me means that the ratio of the damped period to the undamped period is given by 1.25, the original value plus 25%. I can go ahead then and substitute in Td, which is 2 pi over omega n times the square root of 1 minus zeta squared, and divide that by the undamped natural frequency, which is 2 pi over omega n. If I do this, of course the 2 pi on the numerator of each of these will cancel out, the omega n will cancel out, and I'll be left with here 1 divided by the square root of 1 minus zeta squared. What does this mean? Well, it means that 1.25, which we can write essentially as 5/4, is going to equal 1 divided by the square root of 1 minus zeta squared. I can square both sides of this equation, and that's going to give me that 25/16 is equal to 1 over 1 minus zeta squared. And I can invert the fraction here to get that 1 minus zeta squared is going to equal 16 over 25. I can then move this equation around and rearrange it. So I'll have 1 minus 16 over 25 is going to equal zeta squared. And then I can go ahead and play with this and say, well, this is going to give me 25 over 25 minus 16 over 25 is 9/25. So I'll have zeta squared is equal to 9 over 25, which of course means that the damping ratio of zeta that exists is the square root of 9 over 25, which of course is simply 3/5. That means that this system, with the addition of damping, whose period makes it a quarter longer, has a damping ratio of 0.6. A very cool numerical result coming from something that we can often see in the course of experimentation. Don't be afraid to think like a designer and a practicing engineer. That's really what we're here to develop anyways. Take care, everybody.